So we're doing chapter 7 now. Chapter 7. And chapter 7 is all about two types of functions. Lucas, you ready? Oh, so then no, you're not ready. Exponential. So we've already done exponents. And then we're going to do the inverse of exponents, which are called logarithmic. Logarithmic. Such a long word. I don't even know how to spell it. Really, that's how you spell it. We shorten it to logs. Okay? So I like to call this chapter Expos and Logs. Exponential and logarithmic functions. See, I can just stop and write fun, because functions are fun, right? No? All right. Not your kind of fun. My kind of fun. Thank you. Thanks, Camstall. All right. Here we go. 7-1. What we're going to do is we're not going to do any logs yet, so don't worry about the log part of this. Logs are going to be brand new to you. So sometimes whenever you learn something brand new, it's a little confusing at first. We're going to stick with exponentials right now. So this entire first lesson is about exponential functions. And today we are going to have 4 parts, A, B, C, D. But it's really interesting stuff. I think you're going to enjoy this. I don't know. We'll see. That might be a stretch. All right, we're going to start with something that you do not really enjoy probably too much, are the graphs. We're going to do some graphs of exponential functions, and we're going to do these graphs by hand, okay? And let me go ahead and say that this right here, y equals a times b to the x, that is your basic parent function, okay? That's going to be your parent function. And these graphs for exponentials, they kind of all look the same. This is what they look like. They're going to have some kind of a y-intercept. By letting x equal 0, you'll find the y-intercept. And then this is what they do. They're going to go right next to y is 0, and then they shoot up very quickly. Yes. Have you ever heard of someone say, oh, that was growing exponentially, and they sound all smart? It just means it was growing rapidly, very fast. Oh, Kane, can you put that away now? Thanks. All right, you did this in Algebra 1, yes. Now, the tricky thing about this is it has something. This graph has something called an asymptote. I know, right? It's kind of a funny word. The asymptote for an exponential function is just the line y equals 0. An asymptote is going to be something that your graph it's not going to cross, it's going to approach, and they're going to go right by each other forever. It's never going to dip down underneath that asymptote. Okay? And don't draw your asymptotes too fat, because no one likes a fat asymptote. Thank you. I'm here every week. Okay. Number 1. Was that too far? Should I delete that off my video?
No.
Don't let your dad hear that. Okay, here we go, number 1. All right, we're going to graph y equals 2 to the x. Okay, so we're going to see what these look like. And we're going to go old school graphs, which means we're going to make a little T-chart here. But you're really good at exponents now, because we just took that test on exponents. Yeah, you're good. All right, so let's pick some numbers. Let's pick, how about 0, 1, 2, -1, -2. People usually pick those. Those are very basic. And let's plug them in. These are x values. We're going to plug them into our function, and we're going to get our y values outputs. So when I plug in 0, do you remember what 2 to the 0 is? It is 1. Good job. All right, then what's 2 to the 1? Oh, yeah, it is 2. You're right. I don't know why I wrote 1. That was really weird. 2, very good. And then 2 squared is 4. Ooh, it's getting up there. How about -1? What's 2 to the -1? Nope, it's 1/2. Remember? When it's a negative? Yeah, you do. This is.
Oh, that's the inverse.
You just drop it down. Drop it like it's hot. All right, -2 would be 1/4. Okay. All right, so let's go ahead and plot these points. Here we go. Here's our exponential graph. We're going to plot the point 0, 1. Plot the point 1, 2. So right now, if I stop there, it would look linear. But then at 2, I jump up to 1, 2, 3, 4. Goes up pretty high there. Okay? If I went to 3, I'd be way up here at 8. So it's getting big very quickly. If I go over here to -1, I'm at 1/2. -2, I'm at 1/4. And don't forget, remember what I told you, it's not going to touch 0. So there you go. And make sure that you include the asymptote in the graph. It's kind of hard to draw. You might want to draw it in a different color if you want to. That's just so you know that you can't pass that. Pretty good, right? You like them so far? Yeah. Ooh, let's talk about domain and range real quick. Yeah. Domain and range. Okay. Now domain are the x values. On this graph, are there any restrictions to what I can plug in for x? No. I can plug in 0, I can plug in positives, and I can plug in negatives. So the domain for exponential functions is all real numbers. Now the range, the outputs that are coming out of this thing, did you notice all my y's? Are there any negatives? No. You notice that this doesn't go below 0? So my range is greater than 0. Not equal to, that's where the asymptote is, but greater than 0. It's all the stuff above the x-axis. All right, let's do another one, number 2. All right, let's do this one. Y equals 2 times 3 to the x. All right. Now, when you go ahead and plug values in, you need to remember a little thing called Pemdas. And the important thing, bless you, that was adorable. The thing you need to know about Pemdas is exponents before multiplication. Okay? So let's go ahead, let's plug in those same values. Boring. We like boring, right? 0, 1, 2, -1, -2. And we're going to plug these in, and you do the exponent part first, and then multiply it times 2. Okay? So 0 is going in, and I'm getting 2 times 3 to the 0. That is not 6 to the 0. Okay? It's 3 to the 0, which is 1, times 2 is 2. Now plug in 1. 2 times 3 to the 1 is 6. What happened? Explain why? Yeah, there's a couple of ways to explain that. One, I could do this. If I have 4 cubed over 4 cubed, we all know that that's 1, right? Our exponent property says that we take 3 and subtract 3, which is 0. So I don't know if that helps you at all. Or there was another one that I knew of before. It's like 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. How do I go from 16 to 8? I divide by 2. How do I get from 8 to 4? I divide by 2. So then if I divide by 2, 2 to the 0 would be 1. It's another way to look at it. I like that you asked that because it's weird, right? It's like, how is to the 0 power 1? Yeah, so that kind of helps, I think. Or not. All right, here we go. Now plug in 2. 2 times 3 squared is, whoa, 18. You see that? All right, now let's plug in -1. 2 times 3 to the -1 is 2 times 1/3, which is 2/3. And then -2, so 2 times 3 to the -2 would give us 2/9. All right, so in this jumbled mess here, I got to plot all these points. So I have 0, 2. Then I have 1, 6. 1, 2, 3, 4, 5, 6. Wow, this is growing very quickly. And at 3, if I were to do 2, I'm way up here at 18. Okay, and then this goes down pretty quickly. At 1, I'm at 2/3, and then 2/9. So once again, you go right alongside here, and then it shoots up very quickly. Yep, and then you have your asymptote. Pretty good, huh? We will have non-calculator parts in this test, in this quiz, in this chapter, okay? So that's why I'm not doing these on my calculator. I mean, you can. Obviously, your calculator can handle this. But we're not going to do them graphing on our calculator for these. We want to know how to graph these by hand. Okay. Yeah.
Could you plug the numbers into it?
Yeah, but you might not have your calculator, though, at all.
For the quiz?
Yeah, for the quiz. Totally.
Hold on. Time out.
All right, let's do one more. And this one's going to have lots of fractions, so we'll see how this one goes. Y equals 1/2 to the x. Okay, the last two I did, there was a 2 to the x, everything was doubling. There was a 3 to the x, everything was tripling. This is 1/2 to the x. Everything's going to be halving. I don't think that's a word, but that's okay. All right, so here we go. Let's pick those same boring points again for x, our boring values, 0, 1, 2, -1, -2. And let's plug them in. So here we go. We're going to do 1/2 to the 0, which is 1. 1/2 to the 1 is 1/2. Okay, those are pretty easy, right? Now let's do 1/2 squared. What is 1/2 squared? 1/4, good. Okay, so those are pretty good. Let's do 1/2 to the -1. Do you know what that does? 2. Flips everything, right? What do you think 1/2 to the -2 is? 4. Very good. And if you're struggling with that, you can look to see what the pattern is here. Okay, so let's graph this one. All right, so I have 0, 1. And then we have 1, 1/2. 2, 1/4. It's getting closer and closer to 0. If I go on the other side, I'm at -1, +2, and -2, +4. Ooh, see this graph? It's starting out really high and then it's going really slowly down or quickly down to reach the asymptote again. Okay? So we're going to have two types of exponential functions. This is going to be our exponential decay and our other one is growth. Okay? And we're going to see what the difference is between them. All right, so part B. Growth and decay. And they're both good. Everyone thinks decay is bad, but what if you had like some terrible disease in your body and it was slowly making its way out? It's decaying out. That's good. Or you took some bad drugs and they were slowly getting out of your body or something. I don't know. Okay, here we go. Growth and decay. Well, let's talk about both of them. So here's exponential growth. Exponential growth, we drew those two first graphs for exponential growth, so it goes quickly up. Okay? Exponential growth is going to be as x increases, so does y. Y increases also very quickly. And if you have y equals a times b to the x, b is your growth factor. B is going to be greater than 1. Okay? So this is all for exponential growth. B is greater than 1. And we're going to use exponential growth to talk about things like population growth, or money. Maybe your money's in a bank and it's growing. That's pretty rad, right? Yes, I use rad. And then maybe like something like the value of something. Do you have any kind of a collector item at home? Okay, right? Baseball cards maybe, I don't know, something like that. Those are increasing in value exponentially sometimes. All right, then we also have exponential decay. Exponential decay. And exponential decay is going to be as x rises, y decreases. Yep, and that was that last graph that we drew. Okay. For exponential decay, it's the same equation, y equals a times b to the x, except that b is now going to be between 0 and 1. People think like, oh, if it's decay, then it's a negative number. Not true. If it's decay, then it's going to be some small fraction between 0 and 1. Like, I'm getting half of the thing back every time. So that would be a decay. We're going to use this to talk about things like bacteria, or if you've already had chemistry, half-life. Have you had half-life yet? No? Or maybe like the value of something. Like, I heard that the worst purchase you can make is a brand new car. That's what I heard. You buy a brand new car, you drive it off the lot, and it depreciates in value as soon as you drive it off the lot. No. Okay. All right, so here we go. Let's move on. Number 3. All right, this question is going to ask you growth or decay. You do not have to graph it. We want to find the y-intercept, though, by letting x equal 0. Okay? And we just have to say growth or decay. So here we go. Suppose I have an exponential function that looks like this. Y equals 12 times 0.95 to the x. Now, to determine if something is growth or decay, all you are doing is looking at this number right there. The number that the exponent is sitting on. Now, let me ask you this. If you have a school and you're getting 95% of the population back the next year, is that a growth in population or a decay? It's a decay. 100% of the people is the same amount. 95% of the people come back, it's a decay. So this right here is between 0 and 1. This is exponential decay. And the y-intercept would be what? You can do this in your head. The y-intercept is to let x equal 0. 12.
Oh.
0.95 to the 0 is 1 times 12. Y-intercept is 12. What's wrong? It is weird, I know. You don't like that. All right, how about this one? Y equals 0.25 times 10 to the x. Growth or decay? You're looking at this number. You got that right. Okay, that tells us that this is an exponential growth. Okay, you get 10 times as much each time, and the y-intercept is 0.25. All right, what if it's not an equation? What if it's a situation like this? Let's say that you decide to put $1,000 away into a bank account. Okay, maybe it's a CD. Have you ever heard of a CD before?
Yes.
Not a compact disc, but do you know what that stands for? Certificate of deposit. Yeah, you can have different amounts of CDs. You can have a different time frame for a CD. But like, let's say you go to the bank and you want to put your money into a CD. It could be for 5 years. And that means you put your money in there and you don't touch it. Okay, you're not allowed to take it out or else they penalize you. Okay, so you put your money in and it actually grows at maybe 2% interest annually. Something like that. Okay? All right, so would this be growth or decay? Growth, yeah. Yeah, that's pretty obvious, right? Your money's growing, okay? It's a growth, and the y-intercept of this is the amount that you start with, which was $1,000. All right, so that's going to bring us to some real-life situations for growth and decay. Part C, halfway done. Woo. And you might even be able to finish your homework after we're done with this. Okay, so let's talk about some growth models here. We're going to have 2 types of growth models, okay? We're going to have the kind that gives us what the growth factor is, and then we're going to have the kind that give us a percent of growth. So here's a growth factor. You have y equals a times bx, b to the x. I wrote that quite a few times today. The initial amount that we're starting with is going to be the number out front, which is a. The initial amount is a. Okay? The growth factor, because these are going to be growth, the growth factor is b. And time is x. That's our variable. Time's going to be our variable. Okay, let's do one. Here we go. Number 1. These are fun. You're going to need your calculator too. So get your calculator out, ready to go. Because these numbers are going to get pretty big. All right, it says that, suppose you're a biologist. Anybody want to be a biologist? No? Okay. Suppose that you have 100 bacteria, or is it bacterium? I'm not sure. And they began doubling. Gross. So this bacteria is doubling every hour. Wow. So you start with 100 bacteria in a petri dish, and they're doubling every hour. We are going to do a few things. Letter A, we are going to write an exponential equation to describe the situation. Then we're going to find out how much bacteria is in this petri dish after 1 hour, after 2 hours, and then after 1 day. Okay, so here we go. Well, we need to make an equation for this. So here's our equation. Y equals, A is our initial amount. In this case, our initial amount is 100. That's what we're starting with. Our growth factor, I like to put this growth factor in parentheses. Our growth factor is 2. It's doubling. So 2 means to double. And this is raised to the x, and x is in hours. Okay, so it's doubling every hour. Now the first two, B and C here, you can do these in your head, right? If you just think about it. Okay, so it's doubling every hour, so after 1 hour goes by, how many do you have in there? 200, perfect. And if you plug in 1 for x, you will get 200. Now, there's 200. How about the next hour? How much is now in there? 400, doubles, right? Doubles every time. Okay, how about 1 day? Ooh. Whoa, you did it already? Big number, huh? Okay, so you're going to do 100 times 2 to the 24. You have to plug in 24 for x. You do not need to do this in your head. So you're going to go 100 times 2 to the 24th power. I don't need to put parentheses in my calculator or anything like that. My calculator knows to do correct order of operations, and that's the number you get after 1 day. Yes, that's why when people say, oh yeah, it was growing exponentially, it means very rapidly, right? You're growing very quickly here. You went from 100 bacteria, and the next day you walk in and you've got, what is that number? A billion? 1.6 billion? Gosh. What if your money doubled like that every hour? That would be sweet. All right. Now let's talk about a percent increase. So that told us that the growth factor was 2, exactly 2. But sometimes they're not going to give us to us as it's doubling, tripling, quadrupling, stuff like that. They'll give it as a rate of increase. When they give you a rate of increase, then your equation changes a little bit. Okay? It's y equals, A is still the initial amount. It still goes out front. That's what you're starting with. But in here, it's going to be 1 plus r, and then they use t for time. It's still x if you want to say x, okay? So A is still your initial amount. R is your rate. It's going to be a percentage, and you need to change it to a decimal. And T is your variable time. Okay?
Is it 1 plus R?
1 plus R. And this right here, you need to memorize this formula. Hey, girl. Is this money? Daniel? Is this your lunch money?
Well, it's more than
Oh, dang. It's your money for your favorite math teacher? Is that what the money is? No. Okay, I don't have one. All right, here we go. Let's do this now. Okay, let me talk to you real quick about why this is 1 plus R. Let's say that next year people love Valley Christian, and so a whole bunch of kids want to come here. And the increase is going to be a 2%. What if it's a 2% increase on tuition? Is that better? Is that more reasonable?
Yeah,
Okay, all right. Okay, what I'm going to do is I'm not just going to do 2%, okay? I'm going to do this. It's 100% of the tuition that you already pay plus 2% more, right? You have to pay that same amount plus an additional 2%. So I wouldn't want to say my growth factor is 2%. My growth factor is 1.02. Do you get that? Does that make sense? The population is increasing at 10%. your growth factor is 1.10. It's all the people are coming back plus 10% more. All right, so let's do some. Here we go, number 2. Or what are we on? What was that? Oh, I started over with my numbering. Okay, we'll go with that. Number 2. Money, here we go. Suppose you decide to invest $1,500 into an account that pays 1.5% annual interest. Okay? So you're saving for your college, or you're saving for maybe like a really cool Europe trip or something, or, ooh, I know, you're saving for that mission trip you want to go on. So here's some questions. First one, we're going to first write an equation that describes the situation in terms of y and t. Okay? So here we go. Y equals your initial amount, which is $1,500. And then this gets a little tricky in here. It's going to be 1 plus r. Now, r is a percentage. We need to change that to a decimal. Do you remember how to change decimals? Or change a percent to a decimal? Yes.
To the right or to the
2 to the left. To the left, sorry. And then move it over to the left, and you get 1.015 to the t. So that would be the equation that we're going to use to solve these problems. Yes. It's not that bad. Yeah. In this chapter, I do give you some, but that one you do need to know. All right, so let's go ahead and find out how much is going to be in your account. How much after 3 years? Maybe you're planning this trip in 3 years from now. How much money will you have? It's not going to increase that much. Banks don't give you a lot. It's only 1.5%, so don't expect too much of a gain. But there's going to be a little bit of a gain. So you're going to go to your calculator, and you're going to plug it in. 1,500 times 1.015 to the third power. Enter. All right, we are talking about money here, so make sure you round to 2 decimal places. So it's $1,568 and about 52 cents. You can round. Banks usually round down. I want to round up. I want that penny. Okay? And so you've made $68 in 3 years by just keeping your money in the bank. That's not that bad. No. Dang it. Okay. So how much after 3 years? There it is. How much after 20 years? How much after 20 years? You know that you can do this on your calculator. Hit second enter and then just change that 3 to a 20. Saves you a little bit of time. Second enter and then you can type over. Ooh, okay. Yeah. So now I have 2020 and 28 cents. Nice. Okay, now here comes the last one. This is the hardest one. There are 3 ways to do this last part. The question's going to be, how long will it take to have $4,000 in my account? Maybe that's how long it's gonna be a long time though. Okay? How long will it take to have $4,000 in this account? Now there's 3 ways to do this. 1, you can set up an equation and solve it. You don't know how to do that yet because it involves logs. 2, you can use guess and check. Guess and check looks like this. You change the 20 to a 40 and it's not enough. And then you change it to a 50 and then you change it to a 60. It's kind of like, if you ever watch that Price is Right game where you're trying to guess the amount and you're like 50, 60, 70, they're higher, 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 and then you hit 70 like lower. And you got to go back down. It's like that. So let's try 60. Still not there. I'm looking for 4,000. You got it? It's not exactly, but it's just over. Perfect. 67. 66, was that enough or no? Ooh, 66. Yeah, 66. What about 65? No. Okay. So it would take you about 66 years to get, yeah.
Do you put about?
Yeah, you can put about. We're going to find exact answers later. The other way to do this is to graph it on your calculator. You would graph y1 is the graph of the exponential equation. Y2 is the $4,000 amount. And you would find the intersection, and that would tell you an exact amount. I think people like guess and check better, though. Okay, last part. I'm not going to make it. All right, so I don't know my alphabet, so let's go ahead and redo that. Okay, here we go. D. All right, ready? Hi, I'm over here now. Okay. All right, we're going to do exponential decay now. Expo decay. Okay, two types of these. You'll have a decay amount, like a decay factor, and then you'll have a percent of decay. So exponential decay, remember, y equals a times b to the x, and b is between 0 and 1. That's how you can tell it's exponential decay. So this is a really exciting problem. Let's suppose that you win a game show, okay? And after you've paid the taxes and done all that, you have $100,000. Okay? Yeah, perfect. Yep. All right, so you have $100,000. Now, you're excited about this money, and you've decided that you are going to spend 1/2 of the money every week. You're going to have the best couple of weeks ever. First week you go, you're going to spend your money. That's a week. All right, on a car maybe. Really expensive car, yeah. Okay, so here we go. Letter A, I want to write an equation. Always start by writing an equation for these with variables in them so that you can just change your variables when you need to. So here's our equation. Y equals your initial amount, $100,000. Your decay factor is 1/2 to the x. Okay, so here we go. The question I'm going to ask is, how much money will you have after 2 weeks? And how much money will you have after 10 weeks? So x is in weeks. You can probably do the first one in your head. I would hope so. Okay, so you have $100,000. The first week you're going to spend half of that money, so you spend what? 50 grand. Then you spend half of that. Now you're down to how much? You have $25,000. If you plug that into your calculator with a 2 in place of the x, that'll give you that. Now, 10 is a little hard to do because you're going to have to take half of 25, which is 12,500, take half of that. So let's plug it into our calculator. We're going to go 100,000 times 0.5 to the 10th power. Let's see how much money you have. You have $97.66 left. Crazy how quickly that goes, huh? But you had the best 10 weeks of your life, so it was worth it. That's all you got left. You should really invest it, though, and do an exponential growth and grow that money. Okay, the last part. Sometimes we're given it as a percent decrease, too. A percentage of decrease. So the population of a small town is decreasing at a rate of 10%, something like that. Yeah, it's okay. People will die. Here's what percent decrease looks like. Y equals A. Now it's always you're going to take this from the 100%. With growth, it was 1 plus R. With decay, it's going to be 1 minus R. Okay? Remember this. Growth is 100% plus the extra. Decay is subtracting from 1. Because it's kind of like this. Think about it this way. Let me tell you that a shirt that you want to buy at Kohl's is 20% off. Okay? How much of that shirt are you purchasing? 80% of it. So it's really 1 minus 0.2. Okay? If you have a town that is decreasing at a population of 5% each year, how much of that town is really coming back? 95. Okay? So you have to subtract it from 1. All right, last problem. Number 4. Okay, it says here that you decide to buy a car, and your car depreciates in value. Some cars don't depreciate in value, right? Like old cars, and they make them nicer and stuff, yeah. But let's say you buy a brand new car, it depreciates at about 12.5% a year in value, okay? And you bought it brand new for $30,000. Okay? So here we go. We're going to first start by writing an equation that resembles the situation. So we have y equals our initial amount, 30,000. And then we're going to do 1 minus, don't forget to change your percentage to a decimal, 1 minus 0.125. If you need to, you can use your calculator. What is it? 0.875 to the x, or to the t. They like t. You can use x. I don't care. I really don't. Either way. So there it is. Okay. So that's going to be the model for the situation. And so part B, I'm going to ask you, what's your car worth in 1 year? Letter C, what's it worth in 7 years? And the last one, when will it be worth $5,000? When? Okay. Okay, the first two, those are just easy. They're just plug it in. So I've got 30,000, and I'm going to go times 0.875 to the 1. And so after 1 year goes by, my car is now worth $26,250. A little wear and tear. It's got some mileage on it, stuff like that. All right, then we do it again. And this is going to be to the 7th power now. Raise it to the 7th power. And now your car is only worth $11,780.88 after 7 years. You bought it for $30,000. All right. Now, when's it going to be worth $5,000? So you have options here. If you like to graph those on your calculator. The hardest part about that, though, is changing the window. People don't like to change the window. It's hard to change it. Or you can just keep doing guess and check. So what do you want to try? 12 years? I don't know the answer. 13? Let's try 13 years. Okay, let's see. 12 years. Wait, 14 years? Oopsie woo-boos. 14 years. All right, so somewhere between 13 and 14 years, huh? So it's not an exact answer. So it's kind of, you could even go as far as going, all right, maybe 13 and a half years. I'm getting a little closer. But you don't need to do that. Okay, so you can say about 14 years. You could say between 13 and 14. That's fine with me for right now. Okay, they're just estimates. All right.